Hi, in this lecture we introduce dynamic programming through our first example, the coin change problem. The philosophy behind dynamic programming can be summarized with this beautiful quote: "Life can only be understood backwards, but it must be lived forwards." We are going to see exactly what this means later. An interesting question is, where does the name dynamic programming come from? This is a wonderful quote taken from the autobiography of the inventor of dynamic programming. And I'll let you read this, but the bottom line is that dynamic programming doesn't mean anything. It's just a name that was supposed to look nice to politicians. So let us try to understand what dynamic programming is all about, starting with an example. The example is the coin change problem. Imagine that you are a cashier and you have k infinite piles of coins with different values. The values are denoted with the letters D1, D2, all the way to dk, where D would be short for a denomination, but I'm just going to use the word value. So we have k different values, D1, D2, dk. And for each value, we have infinite piles of coins. We're not going to worry about having only a few of these coins. So you can think, for example, in the United States that we have pennies, nickel, dime, quarters, and so on. So you have a customer who buys something and they need some change. You have to give change for some value t, okay? And naturally, you want to be a nice cashier, so you want to use the minimum number of coins, okay? So we can define the cost of t to be the minimum number of coins to obtain the value t. Okay, so for example, if you have three types of coins, k is equal to 3, type 5, value 5, 4, and 1, and suppose that you want to give change for t equals 8, then one possibility is to give change as t equal to 5 plus 1 plus 1 plus 1. This would be a cost of 4 because I'm using 4 coins. Okay, so it's not very nice. A better solution for your customer would have cost 2. T is equal to 4 plus 4, and this thing is optimal. It's optimal because it's clear that you cannot give change just using one coin. Okay, so in this case, the cost of t when t is 8 would be 2. Okay, so what we are trying to do is to devise an algorithm that, given this d1, d2, dk, and give a t, will tell us what is the minimum cost, the minimum number of coins that you need to add to get to t. And later, we are also going to see how to output the actual coins. Okay, so how do we reason about this? Well, the first thing that we do, we are going to try to obtain some kind of recursion. Okay. So how do we go about this? Well, we start thinking along these lines. If we want to give change for t, what can we do? Well, one thing we could do, we could use the first coin, d1. Okay. If I use the first coin, then after I give this coin, I will still need to give change for a t minus d1. Okay. This fact means that the cost of t is at most 1 plus the cost of t minus d1. Okay? The number of coins that I need to get to t is 1 for d1 plus the number of coins that I need to get to t minus d1. This is if we use coin d1. We could also use, of course, coin d2. Okay? So we could alternatively use coin d2. In this case, we will need to give change for t minus d2. And this again will show that the cost of t is at most 1 plus the cost of t minus d2. And so on. We could use coin d3, d4, and so on. So we have several choices, and we ask ourselves, which one do we pick? Okay. Which one do we pick? Well, we pick the one that gives you the best solution. Okay, we pick the one for which this cost here that remains is as low as possible. Okay, this gives this type of relation. The cost of t is equal 1 plus the minimum over I at most k of cost t minus di. Okay. The minimum of cost t minus di, where I range over all the coins that you have. Okay. If you have an optimal solution to change for t, well, you must be using some coin. When you remove the coin, you must still have an optimal solution for the remaining value. This is captured by this equation here. Okay, so now we have this recursion, written this recursion right here. Now, we will be tempted to just write down a straightforward recursive algorithm, but this would be a false start. Okay, so a false start would be a naive recursive algorithm which simply calls itself recursively using this recursion. Okay, the algorithm to give the answer for t will just return the minimum of the algorithm of t minus di for I at most k. Okay, this is natural, but it's not the right thing to do. Why is that? Well, what would be the running time of this algorithm? Well, even if you just have two coins, so k is equal to 2, and the first coin is, say, 1, and the second coin is 2, the recursion would obey something like this. T of t, the running time to give change for t, would be at least t of t minus 1 plus t of t minus 2, where these two come from using coin 1 or coin 2. Okay? And then if I want, I can further expand this t minus 1, again with the recursion. Okay? And you will get t of t minus 2 plus t of t minus 3 plus the previous term that I had here. And this thing clearly is at least twice t of t minus 2. So you get at least 2 times t of t minus 2. And this is a very bad recursion to have because its solution grows exponentially with t. Okay? This would imply that the time to give change for t is at least exponential in t. Okay? And this is very bad. Okay? As we discussed earlier, we don't want to give exponential time algorithms, we want to give something much faster that can be used. Okay? So here is where dynamic programming kicks in, really. The critical observation is that we're doing something very stupid. We are solving over and over again the same problem. Okay? We should stop solving over and over again the same problems and just solve the problems once. For example, if you go back to the recursion here at the bottom, you had two occurrences of t minus 2. Okay? And if you think of that, what it means is that you're solving twice the problem of giving change for cost t minus 2. Okay? But this is not very intelligent. You should only do this thing once. Okay? And that's what dynamic programming does. Okay? It's only going to solve every subproblem once. Okay? And once you have this idea, then you can write down a fairly simple iterative algorithm, which works as follows. So the algorithm to give change for t would use an auxiliary array, c from 0 to t. We are going to initialize c of 0 to 0. And c of I would be the cost to give change to I. Okay? And then we are simply going to fill the array from the smallest value to give change for until t. So we have this index s that goes from 1 to t. For every value of s, we pick, we let m be in the minimum of c of s minus di. For every I such that s minus di is bigger than 0. Okay, so this would be the cost that you're left with if you're using coin DI to solve the problem of to give change for S. Okay? And then the S entry of the array would be 1 plus this minimum. Okay? The running time of this would be order of t times k. This outer for loop takes t iterations, and computing this minimum takes k, because you go over k possibilities. Let us illustrate this with an example. So here is an example. We have 3 coins with values 5, 4, and 1, and we have to exchange for 8. Okay? And here is our auxiliary array C. Okay? It has entries from 0 to 8. And then we initialize the first location to 0, and then we fill it from left to right in this way. So we begin with the first location, 1. If we want to give change for 1, well, there is only, so if you use a coin 5, we will go outside of the array. That's not taken into account in the minimum. Same for coin 4. So we can only use coin 1, okay? In this case, we will be left to giving a change for 0, which has a cost of 0. So the cost of 1 is 1 plus the cost of 0. The cost of 0 is 0, so it's just 1. Same thing for 2. Okay? The only coin that we can use here is the coin with value 1. So the cost of 2 would be 2. And similarly, the cost of 3 would be 3. Things get more interesting in the case of 4. When you go to 4, then you have multiple choices, okay? The cost of 4 by our recursion is 1 plus the minimum of the cost of 3, using a coin with value 1, and the cost of 0, because I can use the coin with value 4, which will get me all the way to 0. Okay? So the cost of 0 is 0, the cost of 3 is 1. Sorry, the cost of 3 is 3. So the cost of 4 is 1 plus the minimum of 3 and 0. The minimum of 3 and 0 is 0, clearly. So the cost of 4 is 1. Okay, this corresponds to just using the 1 coin of value 4, which takes you all the way here. You get to 5. You have a similar equation for 5. Okay, but now you have 3 choices. So for 5, you could use the coin with value 5, and you're immediately done. The coin with value 4, you go here, or the coin with value 1, you go here. You compute this minimum, and the answer is 1, so you put a 1 here. Cost of 6, again you have 3 choices. The coin with value 5 will take you here, will take you to 1, which has a cost of 1, and that's the minimum choice. So the cost of 6 will be 2. Okay. Another possibility would be using first the coin with value 1 will take you here, and then this thing has cost 1. So you would again get 2. It would not be good to use the coin with value 4, because it will take you here, will take you to 2, which has cost 2, and so you will get something bigger. If you go to 7, again, you could use the coin with value 5, it will take you here, which has cost of 2. The coin with value 4 will take you here, which has cost of 3. And the coin with value 1 will take you to 6, which has cost 2. Okay, so you compute the minimum, you get 3. You put your 3 here. And then finally, what we wanted was to give change for 8. Okay. And here you could use the coin with value 5. Okay, it gets you to 3, but 3 has cost 3. Okay, and that will give you a cost for 8 of 4. Okay, alternatively, you can use the coin with value 4. That gets you to 4, which has cost just 1. That will give you an overall cost of 8 of 2. Or you use the coin of value 1, which takes you to 7. 7 has cost 3, so that will give a cost for 8 of 4. So the minimum of this thing is 2, corresponding to the choice of using the coin with value 4, go here, and then using again a coin with value 4. So far we have computed how many coins we need. Now we also want to know what these coins are. For example, to give change for 8, we want to know that 8 is equal to 4 plus 4. We want to actually output these values. And there exists a general way in which you can modify a dynamic programming algorithm to also print the solutions. Here is the previous code to compute the cost in green. And we are now going to add some few lines in purple to obtain another algorithm, algorithm 2, okay, which can also be used, whose output can also be used to print the solutions. We're going to use another auxiliary array A from 0 to t. Again, A of 0 will be set to 0. And basically, the idea is that A will contain not the minimums, but the arg minimums. So after you compute the minimum, just like before, we're also going to compute the arg minimum, which we denote by I. Remember, that's the value of I that gave the minimum. Okay, so basically it tells you which coin you used, and then you fill the est value of A with the corresponding value of the coin. Okay. And the general idea is that the values to print are these ones. So first you can print A of t. Okay, this will give you the coin, first coin to use to give change of t. After you use this coin, you have a remaining value of t minus A of t. Okay, so you have to give change for this, and the coin to be used for this would be A of t minus A of t. Okay, and you continue in this way until you finish. And here is the pseudocode that will print the coins after you have run the previous algorithm. So to print coins for t, you will start from I is equal to 2t. You print the ith entry of the array A, and then you subtract that entry from I, and you iterate until I gets to 0. So the time for this is linear in t. Let us visualize this with an example. Here is the example from before. You have 3 coins, you want to give change for 8, so here is how we fill the array C before. And below A are the corresponding argmins, meaning the value of the coins that gave the minimum. Okay, so for example, you know, for 1 you have to use a coin with value 1. For 4 you have a cost of 1 if you use the coin with value 4. With 5 you have a cost of 1 if you use the coin with value 5. And for 8 you have a cost of 2 if you use the coin with value 4. Okay, so this will be the first coin to output 4. We output here, and after I output this, I go to a value of 4. So then I ask which coin do I need to use for this, and again will be told here that you have to use a coin 4, and this will be the other 4 here. Then you get to 0 and you're done. And to give another example, here's what happens for 7. Okay, 7 has a cost of 3. Okay, the first coin to use is a cost 5. This would take me to a value of 2. 2 has cost 2, and the first coin to be used will be the coin 1. So you output 5, 1. Then you get here. Again, you have to output the coin 1. You output this thing here, and then you're done. And here is how you output solutions in dynamic programming. And now we can summarize what the steps are for dynamic programming. So the first thing to do is to identify some subproblems. Okay, so in the coin change example, the subproblems were all the costs from 1 to t. Okay, here they're fairly natural, but in some cases they may be less natural. And the catch here is that although we just want to give change for t, we're actually solving all these subproblems from 1 to t. Once you have the subproblems clear in your head, you can write down a recursion. We can try to obtain a recursion. And this is also known as a structure of solutions or the optimal substructure property. In our case, the recursion was this equation here. The cost for t is 1 plus the minimum of the cost t minus di for every I at most k. Once you have these two, then the algorithm is just going to solve all the subproblems only once. Okay? The running time that you will get is the number of subproblems, which is t in our case, in our example, times the time to compute the recursion. And here the time is order of k, because it is minimum here. So in our case, the running time is t times order of k. Okay, and as a final comment for this video is that we just saw dynamic programming as an iterative or bottom-up procedure. So you solve all the subproblems from the smallest to the biggest. Okay, we started with cost 1, then cost 2, and so on. But you can implement any dynamic programming algorithm in a top-down or recursive fashion. For this, you keep a list of all the subproblems that you solve. And at the beginning, every time that you recurse, you're going to check if the subproblem that you want to solve was already solved. If so, you just read off the solution and you return. Okay. This way of doing things, the top-down or recursive fashion, is called the memoization. And recall that even for divide and conquer, we saw two ways of writing down algorithms. You could write them in a recursive or top-down fashion, or in iterative or bottom-up fashion. And typically for dynamic programming, it's a little more natural to write things in a bottom-up fashion, while for divide and conquer, the recursive approach is more natural.